Hi all. Let's see the next type of a decimal arithmetic operation, which is BCD multiplication operation. In today's lecture, we are going to discuss about an introduction to what is BCD multiplication and hardware organization of BCD multiplication algorithm, its flowchart with an example. So before looking at the multiplication algorithm, first let us see the list of decimal arithmetic micro operation symbols which are used as a part of decimal BCD multiplication and division operations. So if you look at the symbol of A implies A plus B, it is used to perform an addition operation on two decimal numbers A and B, and the sum is transferred back into the register A. Similarly, B complement. So in case of your sign magnitude operations, you have used a B complement. So in case of complement, it is nothing but one's complement in case of sign magnitude operations. But in case of a BCD operations, B complement is nothing but it performs nines complement of B. Okay. Similarly, if you want to perform a subtraction operation, it is implemented as a plus b complement plus 1, similar to your sign magnitude subtraction operation. So this particular operation, it the contents of A will be added to tens complement of B. So B complement is nothing but 9 plus 1. If you consider it in a sign magnitude, B complement plus 1 is nothing but your 2's complement. But in case of your BCD operations, B complement plus 1 is nothing but your tens complement, where B complement is nothing but your nines complement. So in case of a sign magnitude operation, B complement means you are going to calculate one's complement. B complement plus 1 means it is 2's complement. But in case of a BCD operations, B complement is nothing but your nines complement, and B complement plus 1 is nothing but your tens complement. So this particular micro operation is going to perform an addition operation on the contents of A register to the tens complement of B, and the result is transferred into A. Next is a QL. QL represents the least significant bit or a least significant number of the contents of register Q is represented by QL. So QL plus 1 increments the BCD number by 1. So that is again stored into QL. And next operation is DSHRA, which is nothing but decimal shift right on the contents of register A. It performs a decimal shift right operation on the contents of register A. Similarly, DSHLA performs a decimal shift left on the contents of register A. So these are the list of decimal micro operations, arithmetic micro operations. Next, coming to a BCD multiplication operation. So this is an algorithm that is used to multiply two BCD numbers. So it involves using three registers A, B, Q and a sequence counter. So accumulator register is identified by as register A, and this register is used to perform an addition operation and store the result back into it as a part of your multiplication or division algorithm. And B register is used to hold the multiplicand in case of a multiplication operation, and Q register is used to hold your multiplier in case of a multiplication operation. And sequence counter is used to uh, hold the number of digits of your multiplier. So the number of digits of your multiplier is initialized to your sequence counter. So if you look at the hardware or register organization of BCD multiplication algorithm, there are three registers A, B and Q used in the algorithm, each having their corresponding sign flip-flops AS, BS and QS, which are used to store the sign bits of your register, contents of your registers. And registers A and B have four more bits designated by AE and BE, and that provides an extension of one or more digits of your registers A and B. So in order to perform an extension of your digits of your registers A and B, we have A and AE and BE that is used to provide extension of your one or more digits to your registers A and B. BCD arithmetic unit is used to perform an arithmetic operation on the BCD numbers, and the end carry goes into the flip-flop E. Okay, and the purpose of AE is to accommodate an overflow when you are performing an addition operation of the multiplicand to the partial product during a multiplication operation. So as a part of your multiplication operation, you are going to add the multiplicand to the partial product, and that if there is any overflow out of that multiplication operation, that is stored in AE. Similarly, in case of BE, the purpose of BE is used in the division operation in order to form the nines complement of the divisor when subtracted from the partial remainder. You need to subtract the divisor from the partial remainder by performing a nines complement, and during that it is used to form the nines complement. As a part of forming a nines complement, we are making use of this BE. And the least significant digit of the digit in register Q is denoted by QL. It can be incremented or decremented by 1. So initially BE and AE are cleared to 0. So this is the hardware organization of BCD multiplication algorithm. So there are 3 registers A, B, Q, each having their own sign flip-flops, AS, BS and QS. Registers A and B have 4 more bits designated as AE and BE, which is used to provide an extension to one or more digits to your registers. And the end carry of your arithmetic unit goes into E flip-flop. And the purpose of the digit AE in the hardware organization is to accommodate an overflow in case of multiplication when you are adding a multiplicand to the partial product during a multiplication algorithm. And the purpose of a BE is used during the division algorithm to form the nines complement of the divisor when subtracted from the partial remainder. And the least significant digit of the register Q digit, this is not a bit, the least significant digit of the register Q is denoted by QL. So both BE and AE are cleared to zeros. Next, coming to the flowchart of BCD multiplication algorithm. So the multiplicand is stored in a register B, whereas your multiplier is stored in a register Q initially. Next step is the initialization of your sign bit and the registers. So the sign bit AS, so here the product is stored in A and Q registers at the final of your multiplication algorithm. So you have to assign the sign for your product. So that is performed by performing a sign of your quotient QS XOR BS, which will give you the sign of your product, which is stored in AS. This is similar to your sign magnitude multiplication algorithm. Next, we have a register A, which is initialized to 0. So these are 4-bit registers. So each and every digit is identified in BCD as a 4-bit representation. So A is initialized to all zeros, which is 0000, and B is also initialized to all zeros. This is also initialized to all zeros. And next, sequence counters SC is set to K, where K represents the number of digits of your multiplier. It is not the number of bits, remember, it is the number of digits of your multiplier. Next step of your algorithm is checking for QL. QL is nothing but the most significant, so QL is nothing but the least significant digit of your contents of your Q register. You are going to check QL. If QL is not equal to 0, then we have to add B to the contents of register A, and the result is stored in A. And then you have to decrement the digit of QL by 1. Okay. So after decrementing, again you have to check the value of QL. So this process has to be repeated until QL becomes 0. So if the next time if the QL is not equal to 0, again you have to continue this process and again decrement the value of QL. And next time again you have to check. Let us say at this time the QL is 0. Whenever the QL reaches 0, then you have to perform a decimal shift right operation on the contents of A and Q registers and decrement the sequence counter by 1. And after decrementing the sequence counter, you have to again check the value of sequence counter. If the sequence counter is not equal to 0, you have to go back and start again with the checking the value of QL. So this process has to be continued k number of times until your sequence counter reaches 0. So whenever your sequence counter reaches 0, whatever is there, the contents of A and Q, that will be the product of your multiplication algorithm. So that is your end of your algorithm. So this is the flowchart of BCD multiplication. So initially the entire register A and BE are cleared to 0 and the sequence counter SC is set to a number K which is equal to the number of digits of your multiplier. The next step is the least significant digit of the multiplier which is represented by QL you are going to check it. If it is not equal to 0, then the multiplicand which is in B is added to the partial product which is in A one time and QL will be decremented by 1. So again you are going to check the value of QL and this process has to be repeated until the QL remains 0. So next the partial product and the multiplier. So whenever your QL is 0, the next step is you have to perform a shift right or decimal shift right operation on the partial product and the multiplier and the sequence counter is decremented by 1. So whenever you perform a decimal shift right, you are going to place a 0 in A and transfer the next multiplier quotient into QL. So this process is repeated k times, and whenever since your sequence counter is initialized to k, this process has to be repeated k times to form a double length product which is stored in AQ. So this is your flow chart of your multiplication algorithm. So now let us see an example of BCD multiplication algorithm. Apply two BCD numbers where my first number is 2 and the second number is 10. I want to multiply these two BCD numbers. So here 2 is said to be called as your multiplicand and 10 is said to be called as your multiplier. So represent them in a binary format. So my multiplicand is 2 which is represented as 0010 and a multiplier is 10 which is represented in a BCD form as 0001 0000. So you know how to represent in a BCD. This has to be converted into binary 0001 and 0 has to be converted 0000. So it is represented as a 8-bit representation. And B stores your multiplicand which is 0010. So initially your AE will be clear to all zeros, A will be clear to all zeros and sequence counter has to be set to a number which is equal to the number of digits of your multiplier. So since your multiplier is a 2-digit number, we represent it as sequence counter as 2 and Q holds your multiplier which is 00010000 is your multiplier stored in Q. So this is represented as QL, the least significant digit of your multiplier. Okay. So first we start with checking QL. So QL is equal to 0. So when QL is equal to 0, what we have to do? We have to perform decimal shift right on the contents of A and Q. So we have to perform a decimal shift right on the contents of AQ and decrement your sequence counter by 1. So perform a decimal shift right. When you perform a decimal shift right, the entire bits of this register will shift it towards the right. So here we add 0 and this AE will be shifted towards right. So these entire 4 bits will be shifted here 0000 and these entire bits will be shifted to here. It becomes 0001. Okay, and decrement your sequence counter by 1. So sequence counter becomes 1. So next step, contents are 0000, 0000. Now again check the value of QL. QL is now 1. 0001 means 1. So QL is not equals to 0 when QL is not equal to 0, you have to add B to A and QL has to be decremented by 1. So this is my value of A. Add B, which is 0010, becomes 0010. And decrement the value of QL. QL is 1. When you decrement, it becomes 0. So it becomes 0 means 0000. And this will be 1. Now what we have to do? After performing this, we have to again check the value of QL. So this time QL is equal to 0. So what you have to do? You have to perform a decimal shift right on AQ and decrement your sequence counter by 1. So what happens when you perform a decimal shift right? All these will be shifted towards right. So 0000. Here you get 0000 and all these bits will be shifted towards right, which becomes 0010, and these will be shifted here 0000 and sequence counter will be 0. So since your sequence counter is 0, AQ contains your result. So what is the results of A and Q? It is 0000, 0000, 0010, so which is nothing but 0020. So which is nothing but your 20. So this is your BCD multiplication algorithm with the help of a flowchart. Thank you.